This is video 53 in our series Electrical Circuit Analysis. A reminder, the playlist for all the videos is at the website digital-university.org. In this video, we want to spend some time. It might take like a half an hour or so, but we're not going to go through any equations, but just to try to discuss some of the basic concepts that are involved with inductors and coils and so forth. And we just want to try to show it very basically, these concepts, and probably very crudely, but hopefully it'll be worthwhile for you. Remember that if we have, say, a conductor, and there's a current going through it, through this conductor, that associated with it then, there's a magnetic field. Concentric circles that surround this conductor. And of course, if we had this, say, hooked up to some sort of either voltage source or current source, whatever, let's say we could increase, say, the voltage, which in turn will increase the current going through here, and we could increase it by turning this. And let's say we turn the dial real fast. So that means then that the current going through the conductor is going to increase real fast. So what that means also then in terms of these magnetic fields is that originally they might be like this. But then as the rate of current increases, and I say rate of current, we're going to show that as di dt, the way they do in calculus, the instantaneous rate of change of current with respect to time. We're turning the dial here very quickly, so this increases very quickly. So as a result, the magnetic field gets larger, and there's more flux. There's more of these lines per unit volume of space. And as we increase the current even more rapidly, it's not the amount of current going through the conductor that we're concerned about right now, it's the rate of change of the current. Then this will get bigger as the current increases. And let's say that we've reached our maximum current, so then we might have a conductor like this with a large magnetic field surrounding it. Something like this. Okay, well, suppose now that we had next to this conductor, in fact, let's just get rid of this altogether for a moment and start over. Here we have our original conductor, and then there's another one adjacent to it. And all of a sudden, then we start turning this dial real quickly. So then there would be a magnetic field here surrounding our original inductor, but that magnetic field then is going to be growing. And as it grows, it's going to intersect with this other conductor here. And when that magnetic field, when these lines of flux cross that conductor, the second one, it induces a voltage drop so that there's a current that flows across this. And if this current with the original conductor was in this direction, the induced current in our second conductor will be in this direction. Now, if we get to the point where we stop increasing our voltage source or our current source, so that we have a static situation, that is, here's our original conductor with a large magnetic field surrounding it. And here's our second conductor. It's inside that magnetic field, but the magnetic field is no longer growing, So these lines of flux are no longer expanding out to cut across this. So once we have a steady state here where the amount of current going through here is just at a steady value, there's a static magnetic field surrounding this. But with our second conductor then, there is no induced voltage. So with our second conductor, with our first one we have a large current. We'll just say a large I. But for our second one here, there is no more voltage drop there. There is no more current flowing through it. There has to be a situation where our magnetic field is expanding and cuts across, and the lines of flux cut across the conductor. That's when you have the induced voltage. So for example, suppose that we had this situation then where there's just a steady amount of current going through here. There's a static magnetic field. And with our other conductor, then there is no current flowing through it. Well, now suppose that we had a switch and we just open it up like this, so that now there is no more current going through this original conductor. Then the voltage, the magnetic field that's surrounding it, collapses. Now these lines of flux once again cut across this second conductor. So once again, there will be a voltage drop induced across the second conductor, and once again, in the second conductor, there will be a current flow through it. And the current flow will be in the opposite direction to what it was when we had an expanding magnetic field. So it will be like this. And of course, eventually this magnetic field is going to collapse down to zero, and in which case there won't be any induced voltage here, and the current in this second conductor will also fall off to zero. Now, let's just consider this the same concepts, only not with two separate conductors, but with a single conductor. Only it's wrapped into a coil. And let's say we have this connected, say, to a voltage source, like this, and this is putting out then, well, it's going to result in a current going through here, of course, and we can have a resistor here if we want, so it don't short circuit anything. So let's say the polarity is like this, so that will put out a current like this. And if I'm turning this dial like this, so that I'm increasing this, therefore the current is going to be increasing, so the rate of change of it, designated like this, that too is going to be increasing. Well, now with the coil then, there's going to be, for each one of these turns of wires, there's going to be a magnetic field, and that magnetic field is going to be getting larger and larger. So it's going to be intersecting with these other coil elements here. So just as had in the case of the second conductor, there will be a voltage that's induced, and not in the second conductor, but right in the original conductor here, right in the original coil. And the polarity of this induced voltage is such that it opposes the current that's being fed into the coil from our original source. That's Lenz's law. So one of the things that this means is that the rate of change of a current through a coil, it cannot be as fast as what the rate of change of, say, the voltage is, because we have this opposite voltage that's induced that will inhibit the flow of the current into the coil. And in fact, if you look in the textbooks, you will see that in an inductor, the voltage leads the current precisely by 90 degrees. And in the next video, we'll explain this more analytically. But we'll actually use some elementary calculus for that situation, and we'll show it explicitly that in a coil, the voltage leads the current by 90 degrees. What we want to just show right now is that, remember, Lenz's law is that this induced voltage opposes the flow of current that's coming into the coil. Now, let's just suppose that we had a very simple situation. We had a constant current source. So a coil hooked up to a battery. So we just have a battery. There's a resistor. And then we have our coil. Okay, and let's say this is just 10 volts. And this is, say, a resistor of 2 ohms. Now, as we just discussed, there will be a voltage across the coil. And remember, the voltage is equal to, or it's proportional to, the rate of change of current. In our original diagram, we had a varying voltage source. Like this. And we could, say, increase it by turning the dial, which meant that we had an increasing amount of current. So di dt was positive. And that makes sense now that the voltage across the coil here should be proportional to this, because if this is positive, that means that the current is increasing. If the current is increasing, it's getting stronger, and that means then that these lines of magnetic field are getting larger and larger, and they're going to be intersecting across these coils here. Of course, that's what induces the voltage. So it is proportional to the rate of change of current, and in fact, there's a proportionality constant, and that's called the inductance of the coil. And for each coil, the inductance depends upon the number of turns in the coil. In fact, it depends upon the square of the number of turns. It depends upon the circumferential length of the coil. It depends on the area of it and so forth. So each coil has a unique amount of inductance associated with it. And remember, the inductance is measured in henries, where 1 henry, it's a volt times second divided by amps. It seems like a weird unit of measurement, but you see, if we take this, volts times second, that's 1 henry, times the rate of change of current, that's amps per second, this cancels, and we get volts. Okay, but let's go back now to our situation here. So let's just say that there's a switch, and at time t equals 0, we throw the switch, so there's a connection here. Now, at the instant after we throw that switch, say at time t equals to 0 plus, we mean instantaneously afterwards, what will happen is there's such a bare amount of current coming across the resistor here that there essentially is no voltage drop because the current is so small. Well, now if Kirchhoff's voltage summation law is going to hold true, then that means there has to be a voltage across this coil here that's going to be equal to 10 volts. And how can that happen? Well, remember, the voltage here in the coil equals L di dt. So let's say, for example, this had an inductance of 2 henries. So we see that the voltage that's across this coil it does not depend on the amount of current going through it. It depends on the rate of change of the current. So before it was 0, now it's just a trickle, but that is a rate of change going from 0 to some value. And in fact, at this instantaneous moment in time, right after the switch is thrown, the rate of change in the current will be 5. So that 5 times 2 is 10 volts. And it also has this polarity because of Lenz's law. This has to have a polarity so that the induced voltage opposes the current that's being fed into the coil. So immediately after if we have a switch here, immediately after we throw that switch, for just an instant in time, there's a voltage across this coil here of 10 volts. Then what happens is, of course, the current rises to more higher values. So the current is still changing, but the rate of change of the current in the coil decreases. So as the current gets bigger, its rate of change gets smaller. As its rate of change gets smaller, as this number gets smaller, then this decreases from 10 volts, 9.99 volts to 9 volts, and so forth, which means more and more current. So now there's a larger and larger voltage drop across here. And eventually, of course, what we're going to have is just 2 amps of current going through here. There's a voltage drop across here. Now this induced voltage that we had in the coil, that's gone then, because we have just a steady amount of current here. Therefore, there's no expanding magnetic field. There's no longer an induced voltage. So if we look at it like this for the coil, say this is voltage and this is time. Originally it was 10 volts, and then it falls off like this. And again, in the next several videos, we'll have equations here where we can solve for this curve explicitly. And the amount of current in the coil over time, that looks like this. It starts at 0, then goes like this, till it has a value of 2 amps. Well, this curve here, it looks more like maybe this. It gets flatter and flatter as you go along the curve to finally it's just a horizontal line. So what this shows us is that the rate of increase of the current is getting less and less and less, and that's why the voltage is falling off more and more, because the induced voltage depends on that rate of change of the current. And again, we'll be discussing all of this in more detail in future videos, and we'll have exact equations that will describe all this for us. One other thing we want to mention, suppose that we had our circuit here. It was like this. $10 volts, 2 henries, 2 ohms. And it's been running, so here we have 5 amps going into it. There's 5 amps going through here. There's a voltage drop across here of 10 volts. Incidentally, when we had this induced voltage, we indicated it back when we were right here, just after we'd thrown the switch. We indicated it with these circles around it because this is not a voltage drop now in the coil. This is an induced voltage. This, of course, is a voltage drop across the resistor. Okay, now suppose we have this circuit here, and then all of a sudden we can throw a switch so that the voltage source is no longer there. There's no voltage source. There's going to be no more current being supplied. So now it's like this. So say at time t equals 0, then we threw a switch, so the voltage source is gone. At that moment in time, there is 0 current going through here, but there is 5 amps of current going through the coil, just at time t equal 0 plus. We had a battery here, we threw a switch, now there's no more current source here. At that precise moment in time, there's still 5 amps of current in the coil. And the reason for that is, when we take the voltage source away, so now the current source is cut off, but remember that when we had this sort of steady state condition, when we had 5 amps of current flowing through here, there was a magnetic field across here. It wasn't expanding, so there wasn't any induced voltage, but there was a magnetic field across this coil. Now when we take the current source away, that magnetic field will collapse. What happens when it collapses? So we have a large magnetic field, and when it collapses, when it gets, it might be like this, but then when it collapses, so it gets smaller and smaller, it's going to cut across the wires in the coil, and what does that do? That gives us an induced voltage. The polarity of the induced voltage is like this. It is of opposite polarity to what it was when the current was expanding in here. Remember, initially, when we had an expanding current going through here, we had an induced voltage like this. Eventually, that fell off to 0. Well, now when the magnetic field is collapsing, now it gives a reduced polarity here. What this will do is, this will drive a transient decay current through the circuit in this direction. It'll start off at 5 amps, but of course it doesn't stay like that. Our decay current will look something like this. This is 5 amps, and it falls off to 0. But there is a decay current, and notice that the direction of the decay current, it goes around like this, and it flows through the coil like this. Well, that's the same direction as the current was through the coil when we had it hooked up to the battery. So for the decay current, or what they'll call in the textbooks the decay transient current, the direction of it through the coil is the same as what it was when we had it hooked up to a voltage source. We want to point that out now because we're going to use that fact in the future videos when we discuss inductor resistance circuits in more analytic detail. Anyway, that's it for this video. So we just want to sort of qualitatively discuss Lenz's law, the fact that in a coil the current lags behind the voltage by 90 degrees. We'll show that explicitly in the next video, and that you can have decay transient currents, and the direction of these decay transient currents through the coil are exactly the same as what they were when the coil was hooked up to a voltage source. So anyway, come back and join us for the next videos. We're going to go through this same concepts, and we're going to do it more analytically, and we'll get a chance then to use some of our elementary calculus.